This is the lecture about population sampling, and in this lecture we will discuss about the s- the the reasons, the rationale of doing the sampling, the purpose of doing the sampling, and some of the very important nomenclatures that we use in it. And in the end, we will discuss about the sampling distributions. Basically, this lecture is part of the course from statistical inference, which is taught in different universities and often sometimes called as the statistics 2 or business statistics. Normally, in introductory courses of statistics, like Introduction to Statistics or Probability in Statistics, we seldom talk about these things. But if you are taught about population sampling and sampling distributions in your course, whether it is an introductory or an advanced level, then you can also take help from it. So, population sampling. Population sampling is the process of taking a subset of subjects that is representative of the entire population. So, this is a very important point to understand. Suppose we have a huge data and we have to analyze it, but for some reason or the other, we cannot do. Most probably, the reason could be that the data is so huge in quantity, like it has thousands and tens of thousands and sometimes millions of values, that it is impossible to analyze each and every single value in the data set to draw conclusions about it or to interpret it. If that happens so, then what statisticians do or what the data analysts do is this, that they take a group, a small group from the data set that is to be analyzed. This group that is taken out is also called as the sample. It is also called a subset, and the analysis is basically done on that group or on that sample. Now, this could be more than one groups or this could be more than one samples. Though we are doing the analysis on the group or the sample that we have taken out from the bigger set, but our purpose is always to analyze the bigger set using that small group or the subset that we have taken. Now, this process of doing the sampling or doing the taking the group from a huge data set is basically called the sampling process. Now, since the objective is not to analyze the group, rather to analyze the huge data set, which is also called as the population, therefore, it is very, very important that the sample that we have taken out of the population should represent the population as well. If it is not representing the population, then the whole analysis could be wasted. So sampling should be done in such a way that it should be representing the population. Now, we won't be discussing the sampling techniques over here, but we should know that your overall result heavily depends upon how good the sample was. And when we say how good the sample was, it basically means how good it was representing the population. If it is not, then everything is wasted. For example, let's say that I'm an entrepreneur and I want to launch a new product in the market, but I have set certain standards about that product, and I know that my product is going to be very expensive. Therefore, it will only be I'm only targeting the that that part of the population or that specific part of the population who can afford it. Let's say that my product is a deodorant or a perfume, and a single 100 ml bottle of it costs around 15,000 rupees. Now, I hire a market researcher and I asked him that I want to see that how the feedback or the response of my product is going to be. Therefore, I want you to do some survey analysis. He said, okay. Now, in order to make a survey about my product, although he knew that it's an expensive one, but suppose that my market researcher is a sort of a lazy person. He said, who cares about going to some specific area of the city? He just, opened the door of his house, went out, and picked up 10 people which he saw first while he was walking outside the street. Now, coincidentally, the people that he picked to do the survey were those who had an average salary of 10,000 rupees per month. So definitely they can't even dream of buying that product. So the sample that he took in order to analyze the population that was um, that was that was that belonged to the people who should have very high living standards definitely could not represent it. So although the sample was taken, but it did not belong to the population that it was meant to be. Therefore, probably the survey result would result in a negative feedback to the product, and definitely this could stop the launch of my product, taking it into view that people don't like it, are not going to be liking it. So sampling is very very important in any research, in any analysis, in any quantitative or qualitative data analysis. The sampling process must be done very cautiously, very, very properly. Now, there are different characteristics of the sample that warrant it to be representing the population, but the very most important characteristic of the sample is this, that the size of the sample should be huge, because it is natural that larger the sample size is, the more would be the probability of representing the population. So we try to take the sample as much higher in size as possible. So if the sample has been taken properly, it would be representing the population, and definitely it would ease us to understand the population. It will save time, money, and effort while conducting the research. So, but every researcher should always keep in mind that an ideal scenario would be to take all the individuals of the population to analyze it. And sampling is only done because this is not practical way to do of doing the things. Let's understand this sampling, uh, the concept of the sampling, the mathematics of this sampling in with a simple example. Suppose, this example will also help us to understand the concept of population too. So suppose I have some data set X, and it has these values like 1.2, 1.3, 1.1, and so on till 1.8, and I want to basically analyze this X. Now, if I take every individual value in X to analyze it, then X would be termed as the population. But let's say that I randomly pick few values of X from the X, and suppose they are 1.2, 1.3, 1.5, like this. Then this X1 that I've taken from X is basically called my sample or a group or a subset of X. And the analysis on this X1 is basically the analysis that I am doing on the sample. But as we said earlier, that although we are analyzing the sample, but our objective is always to analyze the population. So after doing the basic statistical analysis on the sample, for example, the very more important thing after doing this analysis on the sample is this, that how we are going to generalize our results on the sample, from the sample onto the population. So this is very important part, and this is the main thing that creates the troubles, because it's easy to do the statistical analysis on a data set, whether it is a population or a sample. But the main problem arises that, how good we are to generalize the results from the sample onto the population. If I take the mean of the sample, for example, then how can I understand or estimate the mean of the population from the sample mean? If I take, if I find some variance of the sample, then how can I use this variance of the sample to find the variance or estimate the variance of the population? This process of finding the values, finding the statistical parameters of the population from the sample, or generalizing the results from the sample onto the population, is what we actually call statistical inference or inferential statistics. So this is the basic difference between descriptive statistics or general statistics that we call, and then inferential statistics. And this is also a research process, also sometimes called as a research triad, that firstly we have some population available, we take a sample out of the population, we analyze the sample, we get the results, and then we generalize these results onto the population. Or better understand it in this way, that suppose this is the population, I mean, we took the sample, which are the orange dots over here, analyze it, and infer the results from the sample onto the population. Now, there's some nomenclature as well that we need to understand regarding the populations and the samples. Usually, Greek letters are used to indicate the statistical parameters from the population, and the English language alphabets are used to indicate the statistical parameters analyzed on the sample. But it is not a mandatory thing to do that Greek letters for populations and English for samples. Sometimes we are short of symbols and we can use the same symbol for population and sample as well, but we indicate it either with a subscript or a superscript or something else. The indication should be there. Like for example, let's take some few basic statistical parameters. Mean, let's say, when it is when the mean is taken out from the population, then we indicate it with a Greek symbol or a Greek letter, sorry, called as mu. And when we take the mean of the sample, we indicate it with x bar. When we take the variance of the population, we indicate it with sigma square. When we take the variance of the sample, we indicate it with s square. When we find the standard deviation of the population, we indicate it with sigma, and for the sample s. Correlation is also another very important parameter for the linear analysis between the variables. And for when the correlation is taken for the population, it is indicated with a symbol rho, and when the correlation is taken for the sample, it is indicated with a symbol r, small r. Likewise, regression coefficients, beta for the population, b for the sample, and skewness. Skewness for the population is indicated with S subscript population. Skewness for the sample is indicated S with the subscript sample. There's a slight difference in the calculation methods as well. Let's see them. Let's see first three basic statistical parameters, which is the mean, variance, and standard deviation. When we calculate the mean, taking the data as an ungrouped data statistics, then the mean is determined very easily. That's summing up all the values and divided by total population size. In this case, for the population, capital N is indicating the population size. But for the case of the mean of the sample, it is summing up all the values and then dividing it with the total sample size. Likewise, for the variance, I mean, we are using the population size for the normalizing factor, and but for the sample, there's a difference that we are using n minus 1 as the normalizing factor for finding the sample variance. For the standard deviation, we take square root of the for the variance, whether it is for the population or it is for the sample. Over here, there's something that we need to understand. We need to emphasize upon that the question is that why we are dividing the variance in the sample with the normalizing factor, which is not n, rather it is capital N minus 1. Firstly, we should know this thing that these normalizing factors which we use, whether it is the mean calculation or it is the variance calculation, whether it is for population or whether it is for sample, we call them as the degrees of freedom. Now, this is a very important concept in statistical inference, particularly because this will be, I mean, we will be confronting with it every now and then, so we should understand that what does it actually mean. Degree of freedom basically tells us the number of values that are free to change or free to vary. Now, the concept is very simple. Suppose I have some 5 blank spaces and I ask you to fill those blank spaces with the numbers that you like and find the average of it. Then I can definitely fill these blank spaces with any numbers. I can fill the first blank space with any number, the second blank space with any number, the third with any number, the fourth and the fifth likewise. So I have the freedom of filling all the 5 blank spaces independently. So the degree of freedom definitely would be 5. But let's say that I change the scenario a little bit. Instead of putting the equation in this way, rather I put it in this way, that we have 5 blank spaces and we have to fill them in such a way that the average of those 5 blank spaces is equals to 2.6. Now over here we can see that we have been provided with a constraint. We have been provided with some limitation. And now we should be filling the blank spaces to meet that constraint, to meet this limitation. Now let's understand this example in this way. So suppose the first blank space is this, the second blank space is this, sorry. Let me use the comma over here. The third blank space, the fourth blank space, and the fifth blank space. And what we are saying that the average should be equals to 2.6. Now, if I ask you that what is your degree of freedom to do this thing, then definitely if I ask, I mean, if I start from anywhere, let's say I start from the leftmost corner, then I can fill it with any number that I like to. Let's say I fill it with 7. The second one, again, I have all the independence to fill it with any number. Suppose I fill this one with -7. Third, you can do it with any numbers, like this is 2, this is 1. Now I have to be careful when I reach to the last blank space, because I should consider this thing that I should fill it with the number that should definitely give me the average, which is 2.6. And what would be that number? Now definitely that number could not be any number. It is one and only one number from the set of infinite numbers that would give me the average equal to 2.6. So how can I find this thing? I can find it in this way, that we know that average is sum of all the values, 7 minus 7 plus 2 plus 1, sorry, plus 1. And that unknown number space is the question mark. And we know this thing that the average of all them, average of all these numbers, which are 5 in quantity, should be equals to 2.6. This should give me the average, which is 2.6. Better use the equal to sign. So how could this be done? This is a simple question of mathematics, basic algebra, I guess. So 7 minus 7 is 0, 2 plus 1 is 3. So we get 3 over here plus x that we have to find. And this is basically whole thing divided by 5, and the result should be equals to 2.6. So how can you find the value of x? I think x is now very simple to find. X is equals to, it is 5 multiplied by 2.6, and this whole result then minus 3. So what the answer comes out to be, let's see this thing. The answer can be easily found. So it's basically 5 multiplied by 2.6 and then minus 3. So it is 10. The value of x is basically equal to 10. So that means the blank space should be filled with 10. So let's check it out as well. So 10 plus 2 plus 1 divided by 5 is 2.6. So what was my degree of freedom in filling up these blank spaces? I was basically independent to fill any of the four blank spaces, but for the last one I had to do the calculation. I cannot just fill it with any number. There is one and only one number that could be used, so that means I'm bound to it, which basically means that the degree of freedom is now not 5 as it was in the previous case, rather it is n minus 1, that is 5 minus 1, which is 4. So the degree of freedom is reduced by 1 unit. Now this is the idea of degree of freedom. While calculating the statistical parameters, we have a very simple rule of finding the degrees of freedom. We know this thing that whatever statistical parameter we find, like whether it is mean, variance, or standard deviation on the sample, that the purpose of that parameter is to basically find the corresponding parameter in the population. Like x bar is used to find mu, s square is used to find sigma square, s is used to find sigma. So they are basically estimating those population parameters. They cannot exactly determine them, rather they can estimate them. Estimation means that we are trying to approximate, reach to that value, or it's an idea about that value. So therefore, the sample statistical parameters like sample mean, sample variance, sample standard deviation are also called the estimates. They are the estimates of the corresponding population parameters. So the simple rule that we use in statistics is this, that in order to find an estimate, the degree of freedom depends upon that how many further more estimates are used to find it. Like for example, if we talk about the sample mean, then sample mean is an estimate of a population mean. But to calculate or to find the sample mean, we do not need any other estimate. So the degree of freedom for it is basically n, the total sample size that we have. But if you look into the calculation of the sample variance, in order to find the sample variance, we need another estimate that should have been calculated before. And what is that one? It is the sample mean. So the rule is this, that in order to find the degree of freedom for a statistical parameter, it is equal to the total number of data set size minus the number of estimates that are required to find it. Since in order to find the or to calculate the variance estimate, we need one more estimate to do this calculation, which is the sample mean. Therefore, the degree of freedom for the sample variance is n minus 1, right? If we would have been requiring two estimates to find a particular estimate, then the degree of freedom, or DF as it is often abbreviated as, would be n minus 2. And likewise, it goes on. So this is the understanding of degree of freedom. And taking advantage that we have understood degree of freedom, I want to just focus on um, the calculation of variance from the equation that is given for the calculation of variance, whether it is for population or the sample. We should always remember that variance is nothing but the ratio of two things, which is sum of the squares to the degree of freedom. We can see this thing, that in these formulae we have sum of the squares in the numerators and the degree of freedom in the denominators for the variance case. Like over here, xi minus x bar square, and then summing them from 1 to n, and then dividing it with n minus 1. Likewise in the population variance as well. So these two, the ratio of these two quantities, sum of the squares and degree of freedom, gives us the variance. And it's important to understand this thing because this definition of variance would be used when we will be discussing about analysis of variances or ANOVA, correlations, and as well as in the regressions. So this was about this population sampling. Now we come to the topic, which is sampling distribution. What is a sampling distribution? A sampling distribution basically is a random variable which shows every possible result a statistic can take in every possible sample from a population. It's a very simple concept. And I will try to explain it with, with an example rather than going into the jargons or the subjective definition. Suppose I have a population and I can take out from that population 36 samples of same size, that is 2. Now I have got 36 samples from the population of size 2. Suppose suppose let's say I calculate any statistical parameter on those 36 samples. It could be mean, variance, standard deviation, correlation, it could be anything. Then this means that I have basically got 36 values of that statistical parameter, right? If I make a set of those 36 values of the statistical parameter and I create a data set out of it, then that data set or the random variable is basically called the sampling distribution. If, for example, the statistical parameter was the mean value, then it means I have got 36 different means, as could be seen in the slide as well, and combining or making a set of those 36 different means into one variable is basically called the sampling distribution of the mean. That is abbreviated with capital X bar, and the values of it with the small x bar. So x1 bar, for example, is the sample mean of first sample, x2 bar is the sample mean of second sample, and so on, right? Definitely there would be values in the means which would be coming, which would be repeating, rather coming more than once. So we can also find the frequency distribution in this sampling distribution of mean using the group data statistics method that we have studied earlier before. So let's keep the thing still here, and then we will discuss in the next lecture about the central limit theorem. Thank you very much. Take care of yourself.